Hi, my name is Charles, and I'm here to talk about a tale of two gradients, or comparing exact and stochastic methods for solving optimization problems through contact. I'd like to start by talking about what makes optimization through contact difficult. If we take this cartoon view of optimization, where we have decision variables that we use to set up a simulator, then we define a cost function on the output of that simulator, we can run into a couple of issues. The first is that the simulator contains all of our contact dynamics, which can be very numerically stiff. The second is that we can run into local optima, particularly for more complicated manipulation tasks. When faced with these issues, it's tempting to go straight for a model-free or gradient-free method such as reinforcement learning. If our contact dynamics are stiff, no problem, we can use model-free methods. If we have many local optima, again, no problem, we can use random exploration to get ourselves out of those local optima. However, I think there are a couple of drawbacks with going all the way to a gradient-free method. The first is heavy computational requirements. The second is that these methods can be difficult to debug and tune. And the third is philosophical. I think we're tying one hand behind our back by ignoring the information in the gradient. I set out to answer this question: can exact gradients compete with gradient-free methods for manipulation? To make this comparison, I set up the same simulator, the same cost function, and the same update rule for both exact and gradient methods. These updates are equivalent in expectation. And to get the exact gradients, I used automatic differentiation of a contact simulator. If we look at a simple manipulation task where the goal is to flip this box by 90 degrees, we see that both the exact method and the stochastic method can successfully solve this problem. If we move to a more complex task where the goal is to lift this box to unit height, we see that the exact gradient method is able to successfully lift the box, whereas the stochastic method is unable to find a solution that lifts the box. I think part of the reason for that is that a successful grasp will likely be roughly symmetric. The exact gradient method is able to preserve the symmetry in this problem, even though we don't constrain it to preserve that symmetry, whereas the stochastic method has no way of knowing about that symmetry. If we look at the cost landscape for this problem, it's extremely nasty. There are all sorts of peaks, local minima, it's very stiff. But even so, exact gradient descent can work surprisingly well on this problem, and it works much better than stochastic gradient descent, even when the stochastic method is run for 10 times more iterations. All this is to say, I think that exact gradient methods can compete with gradient-free methods, and they do so quite well. I'm not saying that we need to throw out our reinforcement learning or gradient-free toolboxes. I'm just saying I think we need to think more carefully about how we can use the gradient information to solve manipulation problems. Thank you.